Good morning, everyone. My name is Mudan Wang. I'm a research associate from University of Cambridge, and my presentation is automatic reconstruction of aligned indoor building and facade elements from point cloud data. Currently, there are many existing buildings are very high energy consumption, and they need to be retrofitted to be more energy efficient. Usually, the energy simulation need the geometry information of the buildings, such as the indoor information and also the geometry information of the facade. However, most of the existing buildings don't have the as design or the as built models, and the laser scanning now is a very efficient and accurate method for the data collection to capture the geometry, the information of the buildings for the facade and also the indoor information. And this geometry information and also their spatial relationship are very critical for the energy simulation and analysis. Previous studies have investigated the method of the indoor environment reconstruction, and many other studies also explore the building facade reconstruction. The laser scanning and the photogrammetry technologies are very widely used to capture the facade information. And then based on the point cloud processing, the geometry information of the facade can be obtained. However, currently, limited studies have been conducted to align the indoor and the outdoor elements together. And this information is also critical for the building energy analysis and the retrofitting plan design. So this research aims to develop a method that can automatically align the indoor building and the facade elements from the point cloud. This is the proposed method. This alignment is based on the openings, including the windows and the doors on both the facade and indoor wall elements. As can be seen in this picture, there's a window on the wall, and both the indoor and outdoor point cloud will have the openings on the data. So the input of the proposed method are the facade and indoor point cloud data. And the first step is to identify the walls and separate the walls into individual plans. Then the next step is to detect the openings for both the indoor and outdoor data. And the final step is to align the openings. Therefore, the indoor and outdoor building elements can be linked together. For the wall segmentation, we use the region growing and the Ransack algorithm to do the segmentation. And after the detection of the walls, the next step is to do the opening detection. Compared to the facade, there are more individual walls on the indoor environment. And we don't need to identify all openings for the indoor data, but we mainly need to focus on the openings on the walls that are linked to the facade. So we process the facade point cloud first, and then by comparing the facade with the indoor segmented indoor element building clusters, then using their location and the normal vectors, the corresponding indoor walls can be selected. Then we made the opening detections. And then the final step is the alignment based on the position and shape of the detected openings between the indoor and outdoor point cloud data. And the proposed method is then validated through a real case. This is a picture of the building. This case is a demo site from the EU Horizon Aghili project. This is an old house and has very high energy consumption and need to be renovated to be more energy efficient. The Leica BOK 360 laser scanner is used for the data collection. We select a floor of the building to validate the proposed method. And this is the original indoor point cloud data. And this is the segmented facade walls. We did the segmentation of the indoor walls, and then we used the facade facade data to select the walls that are corresponding to the facade walls. The selection is based on the normal vectors and the position location to do the matching. And this is filled to the indoor walls that will be used for the further processing. And then we did the opening detection on the facade wall elements. The first picture is the input facade point cloud data. And then the second is the facade opening detection. Then we estimate the full coordinates of the facade openings. The results are obtained in the rectangular format. And this picture represents detected openings on the facade point cloud data. And we did the same detection of the openings on the indoor point cloud data. This is the indoor point cloud data, and this is the indoor opening detection. And we also estimate the coordinates of the openings on the indoor point cloud. Then the last step is to align the results of the openings on the indoor data with the facade data. This picture is the alignment results of the openings on both the indoor and the facade data. The detected openings are aligned based on their coordinates representing the openings. The right points represent openings detected in the facade point cloud, and the white points represent the openings detected in the indoor point cloud. And the alignment is performed based on the similarity of the detected openings, meaning based on their locations. So based on the result, there are still some misalignment between the indoor and outdoor opening detection. For example, the largest rectangular detected in the indoor point cloud data, this is not a window. Why is not accurately detected? Because of the occlusion in the point cloud, and this is a very common during the data collection in the indoor environment. And another significant issue is because of the refraction points of the glass in the windows. And this refraction will influence the opening detection, and this is not easy to be avoided during the data collection for the windows. And we need to address these issues based on more enhanced data pre-processing method to remove the noise. And also we need to be careful during the data collection to collect a more complete data. So in conclusion, this research introduced a method that for the automatically align the indoor building elements with the facade elements using the point cloud data. This research highlight the identification and the integration of the openings, such as the windows and doors, so that we can connect the indoor and the outdoor elements together. And also through a real case validation, the results highlight the effectiveness of the proposed method. For the future research, we can focus on refining the algorithms to better reduce the impact from the noise and the occlusions, especially in more complex indoor environments. And also, we need to further minimize impact of the refractive surface during the data acquisition from the Windows data collection. And then we can also consider to integrate more advanced pre-processing techniques to enhance the detection accuracy. And also we can expand the result, this method to more wide range of building scenarios, not just on like one floor. And thank you. And this research is from the funding from the EU Horizon project. Thank you so much.